Welcome. In this session, we'll go through some of the mathematical details of using a local quadratic approximation. To reprise, what we were done is we were given a function that has a scalar argument, and we're going to use a local quadratic approximation. So we'll define a polynomial that has a scalar argument as, I'll use the MATLAB style, where that will be coefficient 1 times the square of the argument plus coefficient 2 times the argument plus coefficient 3. And we can see that there are three unknowns here, and what we'll need are three equations and three unknowns. So the way that we'll do this is we'll say that the user has to give us enough information that we can uniquely determine what those coefficients are. And the way we'll do that is we will constrain this. And the constraints that we'll use are the user will provide us with three estimates of the scalar argument. So the user will have some way to determine what those three estimates are, and we'll accept them as our inputs. So they will provide estimates at argument 1, argument 2, and argument 3. And what we will do is we will require, as part of that, that if we take any of those argument values and we evaluate the polynomial at that, it has to equal the value of the function for that argument. And we'll further abbreviate that as the function evaluated at point I. Let's go through three typical cases. So the first one is provide 3 points. So provide three values of that scalar argument. So we'll call the value of a scalar argument a point. And so we want them to provide 3 points. And if we now write this out, so what that says is polynomial evaluated at number 1 has to equal f1. So I can say that I'll put the f1 here as known, and I'm going to have an equality, and I can see ahead of time that I'm going to have multiple numbers, and I'm going to gather these into some vector form. So the value of the function evaluated at argument 1 has to equal, this will be our first coefficient times the first argument squared plus the second coefficient times the first argument plus the third coefficient. When I evaluate it at the second provided argument value, second provided point, it'll be the same coefficient times, this will be the second argument squared, plus that second coefficient times T2 plus A3. And when I evaluate that at the third point, this will be A1 times T3 squared plus A2 times T3 plus A3. And I can see that instead of having three equality signs, I can gather these values into a vector, and therefore I can gather these values into a vector. And when I do that, I can now conclude that these are the, so now let's think about what is known and what is unknown. Here, the level of the function is known, and here the argument is known. So the unknowns are those coefficients. I can therefore rewrite that as a matrix vector problem to be solved. And the way I like to do it is I like to set this up with to understand what I'm doing. And so this will be a data matrix. These will be known values. This will be the coefficient vector that we're trying to find, and these will be known values. So I can fill these ones in right away, F2 and F3, and now I'll put the coefficient values. So these are the unknowns. So that will be A1, A2, and A3. I can now refer and say, what is A1 multiplied by in the first row? And A1 is multiplied by T1 squared. A2 is multiplied by T1. And A3, well, we might say it's multiplied by nothing at all. I would say it's multiplied by the value 1. It's multiplied by unity. So I'll put unity in here. When I go to the second entry on the left-hand side, I can see that A1 is multiplied by T2 squared. And A2 is multiplied by T2. And A3 is once again multiplied by 1. And now I have the pattern, so I know that that will be T3 squared, that will be T3, and that will be 1. And we can then solve this as a linear equation. And in MATLAB, this would just be, for example, using the backslash operator. So I can, under what conditions, you might ask, is this matrix non-singular? And the answer is when T1, T2, and T3 are distinct. So as long as these are distinct, that is, they're not repeated values, this will have a solution. Now, suppose that what the user does is the user provides 2 points. And this happens quite often. So the user will provide 2 points. And then I say, well, if you give me 2 points, that's only giving me 2 equations in 3 unknowns. So I need an extra equation. And what we'll say is we'll ask that the user also provide us with the first derivative. And for example, this is what we'll do in this course, is this. We will be given the first derivative at the first value, and that we'll write that as the f prime at that first value. So what this would do is the third equation will then become, we want the derivative at the first point of the polynomial to equal the first derivative of the function. That is, we want our approximation to have the same slope at t1 as the function has at t1. And that would imply that this, if we differentiate this polynomial with respect to t, the first one is 2t times a1 times t. So that'll be 2a1, and now I'm saying I'm going to evaluate that at the first point, 2a1t1. The derivative of this with respect to t is simply a2, and then I have nothing that's added because the derivative of a constant is 0. So if you wish, you could put plus 0. I'll omit that. So the system, the linear equation becomes, here, what will happen is we'll copy out the same thing to be sure that we understand this. So the right-hand side is F1, F2, and now I've replaced the third equation, so I have to replace the third right-hand value, and that will be F1, F derivative evaluated at 1. The coefficients are the same, A1, A2, A3. That is, I still need the coefficients for this. And the first two rows are unchanged, so that will be T1 squared, T1 and 1. That will be T2 squared, T2 and 1. And now I replace this third row with this constraining equation, and that will be 2 times T1. A2 will be multiplied by 1, and A3 will be multiplied by 0. And again, if you wish, you can ask, under what conditions are these non-singular? The next thing that I could do is I could provide 1 point. So I could provide 1 point and a first derivative, and then I could also provide a second derivative. And what we would then do is we would have to add, so what we could do, for example, is we could retain this equation, and now we would replace that equation. Or we might reorder them, depending on how we want to structure things. So the constraint, so let's say, following what we've done here, the example is, will be given, so let's suppose we're persisting on point 1, is what we're given is the second derivative of the function evaluated at point 1. So we constrain we constrain P double prime at T1 has to equal F double prime at T1. And that would mean that we have to differentiate this equation with respect to T1, or you could say we have to differentiate this twice with respect to T and substitute T1 in. Those turn out to be the same. So the equation that we need to add is we need the second derivative of P evaluated at T1 to be equal, oh, we've already written that, haven't we? At T1. So that would be we need 2 times A1 to be equal to F double prime evaluated at 1. And our linear equations would then look something like, what I'll do is I'll put these in an upper triangular form, that's my personal preference, is that I'll retain T1 squared, T1 and 1. I notice that this is a 0, so I'll move it up 1, and I'll make that 2 times T1, 1 and 0. And then this constraint equation is that A1 is multiplied by 2, and A2 is multiplied by 0, and A3 is multiplied by 0. And so I have an upper triangular form that's particularly easy to solve by hand. The computer implementation, as I mentioned, is we would simply use the linsolve function or the \/ operator.